Hello and welcome to another episode of Classes with Atish. We will continue with our subject of center of mass, and today I am going to introduce a very important concept of the motion of center of mass. So let us get started. If we have a system of bodies, let's say there is M1, M2, like that, we have n number of particles up until Mn, okay. And from a frame of reference, these bodies are at position vector r1, r2, rn and such, okay. Now, the center of mass of this system of bodies we can write as RCM, which is a position vector, as M1 R1, so position vector of M1 plus M2 R2, and we do all the sums, Mn Rn divided by M1 plus M2 Mn, okay. Now, let's suppose we differentiate both sides with respect to time. So, we will have dRCM dt, okay. And if this is a constant, let's say the total mass of the system is big M, where big M is equal to M1 plus M2 all the way to Mn, okay. We would have M1 dR1 dt plus M2 dR2 dt plus we can go up to Mn dRn dt, okay. Now look at this term. What is this? This is the rate of change of the center of mass. So we can write this as velocity of the center of mass, how fast the center of mass is changing its position. So velocity of the center of mass we can write as 1 by m into m1. Now what is dr1 dt? It is velocity of m1. Similarly, m2 times velocity of m2, and we do the sum mn vn, okay. Now, if I move this term on the other side, mvcm, we can write as m1 v1 plus m2 v2 Mn Vn, okay. Now this is also a familiar term. What is this? This is the momentum of the center of mass, more accurately linear momentum of the center of mass. So linear momentum of the center of mass is vector sum of linear momentum of each of the particles that comprise of the system, okay. So this is a very useful identity that we got, okay. But let me mark this as equation 1, okay. Now let us go back to this. Let us differentiate this equation both sides with respect to time one more time. So we will get dVcm dt is 1 by m1 dV1 dt plus m2 dV2 dt, and like that we go up to mn dVn dt. Okay. Again you will see that this term is nothing but acceleration of the center of mass. And these are the individual accelerations of each of those particles. So we can write it like this. Okay. Now again if I bring m on the other side, so MACM. Now what is this? This is the total external force on the center of mass, or we can say it's the total external force that is on the system. Now it can be possible that M1 exerts a force on M2, and by Newton's third law M2 will exert an equal and opposite force on M1. So if I add up all the forces that are acting on the system, external force, internal force, everything, the internal forces will cancel each other, right? And everything that is remaining will be the external force. So this gives me the total net external force. And what would that be equal to? That would be equal to M1A1, M2A2, Mn So these are forces, external forces that each of these masses are experiencing, or each of these particles are experiencing. Okay. Let me restate that. So these are external forces that each of these particles that is comprising of the system are experiencing. So let us look at, or we can also write this as M1A1 plus M2A2 go up to MnAn. Okay. So F, or let me write sum of external forces, total mass of the system times the acceleration of the center of mass, and this is where it is. This is another useful equation. Okay. Now let us suppose that sum of total external forces, or we can call this as net external force, is 0. Okay. What would that mean? That would mean acceleration of center of mass is 0. Okay. It does not mean A1, A2, An, all of these must be 0. Okay. The vector summation of M1, M1, M2, A2, Mn, An is 0, but individually A1, A2, An may not be 0. Okay. Very important thing to realize here. Okay. Now if acceleration of center of mass is 0, that means velocity of center of mass is constant, not 0, constant, because when we differentiate a constant with respect to time, it is 0. Okay. So velocity of center of mass is a constant. Again, when velocity of center of mass is a constant, it does not mean V1, V2, Vn, these are all constants. They can be variable, but the vector sum of M1, V1, M2, V2, Mn, Vn, those will be constant. Okay. So if Vcm is constant, mass of the entire system is constant. What does that mean? That also means linear momentum of the center of mass is a constant. So if linear momentum is constant, we can write change in linear momentum is 0. This is nothing but conservation of linear momentum. Okay, and we discussed conservation of linear momentum in a separate video. I'll put a link to that. You can go and check out that video for more details. Okay, but realize this: acceleration of center mass is 0, linear momentum is conserved. All of this happens only when this condition is met. So this condition is important, that sum of all external forces on a system must be equal to 0. Okay? Let's look at an interesting phenomena. Let us say there is a projectile that is maybe a cannonball, and it is projected like this with certain velocity v, and obviously under the influence of gravitational pull it will start to follow a parabolic trajectory. Okay. Now let's say midway in the flight, this cannonball, due to some internal stress that has been created, let's say it breaks down into two components. Okay. And if you plot the trajectory of one of those components, let's say it will be something like this, and if you plot the trajectory of the other component, it will be something like this. Okay. All right. Now this is a perfect case of no external force. F external is 0. Whatever caused this breakup of the cannonball was internal forces. Okay. If such is the case, then the center of mass of those two particles that broke down, so particle 1 and particle 2, so particle 1 and particle 2, the center of mass of that two system, if you find out at any point, okay, let's say we are here, okay, and those two particles are somewhere here, the original trajectory of the cannonball before breaking down would have been this line. That would be the center of mass of these two systems. Okay. So the trajectory of the center of mass would have been unchanged. Why? Because there is no external force, there is no change in acceleration. I mean, it's not accurate to say there is no external force, there is gravity force, but that did not change. So whatever the acceleration was there, the velocity of the center of mass will remain constant. So before breaking and after breaking, the location of the center of mass remains unchanged. Okay. Okay. Now it's time to do some problems. So the first problem, I will put it on the board. Mr. V weighing 50 kg and Mr. M weighing 60 kg are sitting at the two extremes of a 4-meter long boat. The boat mass is 40 kg, standing still in water. To discuss a mechanics problem, they come to the middle of the boat. Neglecting friction with water, how far does the boat move on the water during the process? Okay, so let's say here is the boat. okay, and obviously it's on water, no friction. The boat weighs 40 kg. Okay, let me just write it as MB, okay, 40 kg. And then there are two people, probably they are physicists because they want to discuss mechanics. So Mr. M and Mr. V. So Mr. V, he weighs 50 kg and Mr. M weighs 60 kg. Okay. Now what they do is they come to the middle of the boat. So V moves to the right to come to the middle of the boat and M moves to the left to come to the middle of the boat. The length of the boat is 4 meters. Okay. So obviously the middle of the boat is at 2 meters. Okay. All right. The question is, how much would the boat move when these two guys come to the middle of the boat? Okay. First of all, you have to realize that the boat will move. Okay. Why would it move? Because in this arrangement, since there is no friction, whatever force V gives on the boat and M gives on the boat, those are all internal forces because the boat will give an equal and opposite force to V and M to enable their movement. So whatever rearrangement of mass happens in this three body system, any force associated with that is all internal forces. So this is a case where F external is 0. Okay. So if X external is 0, which means there is no acceleration, acceleration of center of mass is 0, or which also means velocity of center of mass is a constant. Now since the boat was initially at rest, so we can say velocity of center of mass is 0. Now since velocity of center of mass is 0, the location of the center of mass is a constant. Wherever the location of the center of mass was, so 40 kg, 50 and 60, right? So it will be slightly towards Mr. M. So let's say this was the location of the center of mass. It remains constant. So which means there is no change. So delta XCM is 0. Okay. Now we know delta XCM, what is the formula? Is mass of V times whatever change in position of V plus mass of M times change in position of M plus, don't forget about the boat, mass of boat times change of position of boat. Okay, that divided by total mass mv plus mm plus mb. Okay. Now we already found out through this reasoning that delta XCM is 0, so this is equal to 0. So then we know delta XV, he moved 2 meters. We know delta XM, he moved 2 meters to the left. Let's assume that the boat will move, let's say L meter to the right. Let's assume that. Okay. And we will also assume that this is our coordinate system. This is the x-axis, positive x-axis that side, and our origin is at the end of the boat. Okay. I should have just lined this up, but think that the origin is at the end of the boat. Now, there is a little bit of catch here. This delta xv, let me write that down. Delta xv, we are saying it's 2 meters, but it is with respect to the boat. So let's write that change in position of v with respect to boat. But with respect to ground, it might be something different. So using our vector notation, we can write change in x v with respect to ground plus change in x ground with respect to boat. So then we get change in position of v with respect to boat. We can also write this as delta x vg minus, if we reverse this, delta x bg, boat with respect to ground. Okay. So now boat with respect to ground, we assumed it as L, and velocity of v with respect to boat, we said it's 2 meters. Okay. So 2 meters positive, this we do not know, delta x v with respect to ground minus L. So delta x v with respect to ground is 2 plus L. Similarly, delta x m with respect to ground will be what? He is moving 2 meter to the left, so minus 2 plus L. And delta x boat with respect to ground will be what? Plus L, because L is to the positive side. Now see here, all of these displacements are with respect to ground, which is, it is all with respect to a fixed frame of reference. Because the boat was moving, we just cannot say v moved by 2 meters to the right. Yes, he moved 2 meters to the right, but the boat also moved L meters to the right. So the total displacement of v was 2 plus L. M moved 2 meters to the left, but the boat moved L meters to the right. So his total net displacement was L minus 2. Okay, so that is what is represented here. Okay, now the problem is simple. Now we can substitute the values. mv is 50 times delta x vg we will have to take. So 2 plus L plus mass of m is 60 times delta x mg, m with respect to ground is L minus 2 plus the boat mass is 40 times it is displacing L. So this is equals to 0. So we can write 10 plus 5L plus 6L minus 12 plus 4L equals 0, or 5 and 6 is 11, 15L equals 12 minus 10 is 2, or L is 2 by 15 meter. This should come out to be roughly 13.3 centimeter. Okay. So yes, we are applying this formula, but understand that these velocities should be all, or these displacements should be all with respect to ground, with respect to one frame of reference. Okay. All right, great. Okay, you can read this question. A man of mass m having a bag of mass small m slips from the roof of a tall building of height h and starts falling vertically. When at a height small h from the ground, he notices that the ground below him is pretty hard, but there is a pond at a horizontal distance x from the line of fall. In order to save himself, he throws the bag horizontally with respect to himself in the direction opposite to the pond. Calculate the minimum horizontal velocity imparted to the bag so that the man lands in the water. If the man just succeeds to avoid the hard ground, where will the bag land? It looks to be a heavy problem, but actually it's not. Okay, so let me explain. So here's a tall building. This height is capital H. Okay, the man has fallen through some height and his remainder height is that is remaining to reach the ground is H. Now there is a pond, okay, which is X distance from the point where he will supposed to land. And this man also has a briefcase with him. Okay, he is an intelligent guy. So what he does is he throws the briefcase to the left. So why does he do that? Because it's an internal force that he is giving to the briefcase, and the briefcase will have an equal and opposite force to the man. Because it's an internal forces, there is no net external forces. Momentum between the man and the briefcase system will be conserved. So to conserve the momentum, the man will get some velocity to the right, and that will enable him to overcome this x distance. Okay. Okay. So let's look at this. So let's say this velocity of the bag is Vb and this velocity of the man is Vm. Now also remember that the man is already falling with certain velocity in the y direction. It's a function of time, it's not a constant velocity. He started from 0 here, but then his Vy is steadily increasing at the rate of half gt square. Okay. So we'll use that Vy after a while, but for now let's concentrate on the horizontal axis, on the horizontal velocities. So we can say, due to conservation of linear momentum in the x direction, we can say mvb is equal to capital M Vm. Okay. So from that we get velocity of bag will be capital M by small m velocity of man. Okay. Now Vm will be responsible to overcome this distance x, and Vm is constant, it will not change. Vy increases but Vm remains constant. So let's say the time remaining for the man to move from here to the ground is t. Okay. In time t, man will reach ground. Okay. So in that same time t, Vm has to carry it just across x. So we can write x is equal to Vm times t. Okay. Okay. Now let's find out what this t is. Okay. Let's say the man took t one time to reach from here to here, and then he will take t time to reach from here to here. Okay. So let's see what is the value of Vy after time t1. Okay. Okay, let's not use t1. We can write Vy square, so V square equals U square, U was 0, plus 2GS, so 2GS is H minus H. Okay? Okay. Now let's look at this journey. So to make, how much time is needed for this journey? So we can use S equals ut, which is Vyt, because we are saying this takes t time, plus half gt square. Okay. If we rearrange this, we can write a gt square plus 2vyt minus 2h is equal to 0. From here we get the value of t is minus 2vy plus minus 1 I am discarding because that negative value of t doesn't make any sense, root over 4vy square 8hg divided by, okay. Now we can cancel out the 2's, so minus Vy plus this becomes Vy square plus 2hg by g. Okay. So we got the value of t. Now if we substitute t back here, so we get x equals Vm times t. Now t is root Vy square plus 2hg minus Vy divided by g. Okay. Now we substitute the value of Vm, or we can write Vm is gx divided by root Vy square plus 2hg minus Vy. Now we got the value of Vm, so we can find Vb. Vb is m by small m Vm, so mgx by small m into root Vy square plus 2hg minus Vy. Now let's substitute Vy. So mgx by small m. Vy square is 2g capital H minus 2g small h. So 2gh will get cancelled. So this will become root over 2g capital H minus Vy is root over 2g h minus h. Okay, we can further little bit simplify. We can write mx root g. If I divide by root g numerator and denominator, we can write this as m root 2h minus root 2h minus h. So that is our velocity with which the bag should be, minimum velocity by which the bag should be thrown so that the man just reaches the pool. Now the second part of the question is how far the bag will land. Now we could do kinematics, but I don't want to do that. We'll be intelligent about it. Why? Because the system of the bag and the man, there was no external force, remember, in the x direction. What that means is the center of mass of the system of the bag of the and the man has to remain same. So the delta xcm, what was the formula? It was mass of the first body, let's say bag, times change in displacement or change in position of the first body plus man times change in displacement of the man divided by mb plus mm. This was the formula. Now, since center of mass does not change, therefore mb times delta xb should be equals to mm times delta xm. Now, delta xm is what? X. So we can write this is big M times X, and this is small m times whatever, okay, we should have done a minus here. So whatever distance the bag moves by, so xb would be minus mx by small m. Now why minus? Because the bag is landing to the left, so the distance is m capital mx by small m. Okay. Okay, let's look at this next question. It's kind of interesting. A uranium-238 nucleus initially at rest emits an alpha particle with some speed. Calculate the recoil speed of the residual nucleus thorium-234. Assume that the mass of a nucleus is proportional to the mass number. Okay. So this reaction is uranium-238. Okay, this emits an alpha particle. Alpha particles have mass of 4 and thorium. So the remaining mass is 234. Okay. So how is this happening reaction? This is a nuclear reaction. This is an alpha emission. But how is this happening is, it's an internal force that is breaking it up. There is no external force. So we can use the principle of conservation of linear momentum. Okay. So therefore, if we know the speed of the alpha particle, so that speed is given as V alpha is given as 1.4 into 10 to the power 7 meter per second, which is really fast. Okay. So we have to find the speed of thorium. Okay. So see, this problem is simple enough. Initially uranium-238 was rest. So because there is, first of all, let's back up. Because there is no external force, F external is 0, so therefore momentum is conserved, P is constant, so therefore Pi is equal to P final. The momentum initially uranium was at rest, and then final momentum, the alpha particle has some mass m alpha. It goes, let's say, with V alpha speed plus whatever the mass of thorium times the velocity of thorium we have to find out should be equal to 0. Okay. So therefore velocity of thorium is m minus m alpha V alpha divided by mass of thorium. Now we can just substitute the values. Why minus? So basically if the alpha particle goes to the right, the thorium nucleus will go to the left. Okay. So mass of an alpha particle is 4 times 1.4 into 10 to the power 7 divided by mass of thorium is 234. Okay. So 2.4 into 10 to the power 5 meter per second. Okay. Okay, that was a simple question. The next question, a cart of mass m, I'll put it up on the board. A cart of mass m is at rest on a frictionless horizontal surface and a pendulum bob of mass small m hangs from the roof of the cart. The string breaks, the bob falls on the floor, makes several collisions on the floor and finally lands up in a small slot made in the floor. The horizontal distance between the string and the slot is L. Find the displacement of the cart during this process. Again, this question looks complicated, but it's pretty simple. So this is the cart, this is the pendulum bob, and here is a slot, and this distance is L. Okay, this mass is m, this mass is small m. Okay. So initially the cart is at rest. Okay. See, when the string breaks, again there is no external force here. So it's the same condition. F external in the x direction is 0. There is some external force in the y direction, but we don't care about y because the movement will happen in the x direction. We can say that the change in center of mass will also be 0 because initially the cart was also at rest, so velocity was also 0, so change in center of mass should also be 0. Okay. Let's assume that this cart moved to the left by a distance x. Okay. So what we'll write? We will write m times the distance m moved to the right with respect to ground. So it moved L to the right, but the cart moved x to the left, so L minus x. This is the displacement of m with respect to ground. Okay, plus the capital M, the mass of the cart, moved minus x to the left. Okay, so this should be equal to 0. So ml minus mx minus capital Mx should be equal to 0. So x therefore should be small ml divided by m plus m. Okay. I hope by now you have enough confidence on this topic, motion of center of mass. We did a few examples. Do leave me a comment if you have any questions or if you want me to solve some particular problems. I will be glad to provide the solutions for those. And with that, we'll end this episode for today. The last topic that we want to cover under center of mass is collisions. And that's a pretty exciting and neat topic to cover. So we will do that in the next episode. See you in the next one.